Hola and bon dia. My name is Rishi Nikhil. I'm from BlueSpec, and I chair the group that is working on formalization of the ISA spec. So the group itself is quite mixed, as you can see from this list here. We have about 10 or 15 people on a weekly meeting basis. You see the people from industry, from academia, etc. I'll just repeat a few slides that I had at the last workshop just to refresh what the purpose is of the formal ISA spec. Everybody's familiar with the 2.2 text document spec and the 1.10 privilege spec, for example, which are textual specifications of the ISA, and everybody uses that to do their creations. But over time, we want to make sure that there's no ambiguities, it's complete. And so the kind of questions you see on the right here, first, people doing hardware implementations, as shown in this box here, are doing some particular implementation. The implementation may be in software like Spike or Kimu, or it could be in actual hardware. And the claim is that this implementation executes RISC-V instructions. And the question is, how do you assure that? Of course, you can do a lot of testing to gather confidence, but is there something more rigorous than that? So an ISA spec is a formal specification of that spec so that there's some formal mechanisms by which we can establish this question. Similarly, people coming from the software side, perhaps a lot more people coming from the software side, writing compilers, just-in-time code generators, etc., have the same kind of question, which is you're starting with some higher level notion of a piece of software in C or Java or something like that, and you're producing RISC-V instructions from it, and the question is, do the RISC-V instructions do what you think it is supposed to do given your understanding of C or Java? And once again, to answer those kinds of questions, a formal spec is a starting point on that. There's a lot of work to do once you have a formal spec, but it's a prerequisite for that. So our goals are the following, and in some sense the second bullet is key. It needs to be precise. That's the whole point of doing a formal spec, and complete. In other words, hopefully it should be able to answer any question you have about what is a legal execution of a RISC-V set of instructions. The formal spec is not just going to be a document that people read, so it needs to be machine readable and executable as well. Although there's some trickiness with executableness because there are choices and options in the instruction set, and so there are variations that can happen in execution. So any particular execution might only be taking one trajectory through the possible executions of the instruction set. But nevertheless, it should admit the ability to do these kinds of things. There's lots of people in the community, and RISC-V is probably a unique opportunity for the community on this, which is to bring a little more rigor both into the hardware design space and into the compiler design space. In other words, there are lots of people who are interested not just in designing a hardware implementation of RISC-V and then assuring themselves that it correctly executes RISC-V, but even deriving that hardware design in a systematic way from the spec itself. Similarly, compilers. You might be able to derive compilers from the spec in a systematic way. This is a little bit more on the researchy end. I wouldn't say it's going to be the majority use of it, but there's plenty of people who are interested in doing that and have been stymied in the past because of proprietary architectures and not being able to have open formal specs of a complete ISA, etc. So RISC-V might be a unique opportunity for a lot of research going on according to this last bullet. And then my top bullet up there is, for me at least personally, a very important thing, which is formal specs and formal methods and things like that historically have a reputation of requiring a PhD to read and understand, and therefore limited to only a small subset of aficionados of formal specs. But I would really like this spec to be approachable by the practicing engineer, the hardware designer, the compiler writer, etc., which is their primary interest, where they can go to the spec to resolve questions about the meaning of the RISC-V instruction set. So as I said earlier, there are plenty of specs. There's English textual specs, there are implementations like this, but none of them really meet all the goals that I described over here. So before I get into the status of things, I'd like to just sensitize you to some of the issues that we face in this group. Unlike the ISA design itself, which is riding on 5-6 decades of experience in ISA design through the years, this particular topic of fully specifying in a formal way the instruction set is actually fairly young, even in the research community. So there's not much literature to go on this, and there's not too much guidance on exactly what trajectory one should take to solve this. So one key issue is modularity. So as Krista mentioned in his talk, right at the beginning, it's perhaps the most modular of ISAs. It's like a Lego set of different options that you can choose which options you want in plugging together your particular configuration within this ISA. So you can see listed up there in the bullets a bunch of different choices that one can make in a particular implementation. And even more than that, some of you may know this already, but some of these are even technically dynamically selectable. You can switch on and switch off, for example, your floating point support, or whether you have compressed instruction support, etc. Now, most implementations typically are not that flexible. They pick a particular selection of these things, and it's wired in. And so you can imagine a very specific thing for that. But as a formal spec, we need to be able to accommodate dynamically fitting in these things and explain what it means to dynamically switch on and switch off some of these options. So this is one of the challenges. And as you parameterize more, it might start getting a little more obscure. So how do you keep it readable despite this modularity? So again, I'm not aware of there being much literature on this. So in some sense, we're breaking new ground in addressing an issue like this. Second issue is, of course, extensibility. It's not, RISC-V ISA is not frozen in stone, as you've seen today and tomorrow. There's still extensions being developed. So the spec eventually has to accommodate all these standard extensions. And being an open ISA, people are going to be doing their own extensions over time, and they would presumably like to build on top of whatever formal spec we come up with to add their own specification of their own particular extensions. A third issue is concurrency and non-determinism. So one aspect about the ISA is just to think of precisely specifying for each instruction, what does it do, and you just think of one instruction at a time. But in real implementations, we exploit concurrency heavily, of course, certainly through pipelining, but also through out-of-order execution, speculation, and so on. And when you have this kind of concurrency, and you also have a weak memory model, about which you'll hear more in the next talk, then you can get different behaviors for the same program, even on the same implementation, on different runs of the same program, and certainly across different implementations across it. So these are allowed variations in behavior, allowed meaning within, in some sense, within the spec. And so, and if you just think of the instruction set as just one instruction at a time, you don't really get very much very interesting behavior. So in the spec itself, you need to be able to accommodate the idea that we will be driving this weak memory model with some degree of concurrency in it, and we want to be able to capture what are all the allowed behaviors in this. So this is the third issue I just wanted to bring up. So coming to the status. So one of the things that the foundation did early on, which I think was a good decision, was to split the overall formalization into two separate groups. the group I'm talking about now, which is the ISA formalization, and the talk that you'll hear next from Dan Lustig, which is about the memory model thing. And the reason is because these two subjects are in of themselves quite major subjects to deal with. And further, they're reasonably separable. In other words, you can talk a lot about the memory model without getting into the details of the ISA, and vice versa. You can talk a lot about the ISA without getting a lot into the details of the memory model. So that's one point. So we're just focusing on the ISA part at the moment, and it's still future work to be integrated in with the memory model, about which you will hear in the next talk. So the other thing is, because there is no great literature support and experience in this level of complexity, lots of people have done formalizations of small toy ISAs and small toy settings, etc. But to do it for a full industrial strength ISA with a full industrial strength weak memory model is fairly new. So it's not quite clear exactly how these things should be modeled, etc. So we actually, within the group, whose members I summarized on my first slide, many people have different ideas on how we're going to achieve all these goals. And so little subgroups with a lot of constant discussion amongst them are actually pursuing many different approaches. And I think what will happen is, as these efforts mature and we're then able to compare them both informally in terms of things like readability, etc., but also formally in terms of expressive power, etc., I think it might clarify over time as to what the best approach will be for the RISC-V ISA itself. So there are many different projects going on with our slightly different takes on those issues that I mentioned in my last 3 slides, particularly about concurrency and modularity. So one of the Haskell projects, when I say Haskell programming language has been chosen by a couple of the approaches here, because it's a pure functional language, it has very simple semantics when used in as a simple functional language. And one of the teams is led by the team at MIT, and which is sort of furthest along in terms of how much they have covered of the kinds of things we're modeling in the ISA. And you can see in the first bullet there the level of coverage so far in what's been done. And there was a tutorial on this yesterday by Thomas Bourgia, who's in the audience perhaps. Thomas? I don't see his hand raised, so maybe he's not here today. Anyway, he's here for the workshop, and he's the key developer of that version of the semantics, and he had a tutorial yesterday during the tutorial day. So that particular thing, you can go and see the code itself, the Haskell code for it, if you go to the GitHub URL that I have listed up there. And it's already in use principally at MIT, but a little bit outside also, in ways that you can see in those 4 bullets. So first of all, it's Haskell. You can just run it as a Haskell program. It's an executable simulator. You can load an ELF binary, or you can load a memory hex binary and just execute it and see what happens. And in that form, as an executable, one of the initial uses is as what we call a tandem verifier. So if you have a hardware implementation or a software implementation of RISC-V, and if you can, at the execution of each instruction, produce a certain packet of information about what changed due to that particular instruction execution, we can compare that with the change in the formal model to verify that the change is what the formal model says it should be. And that's one way to quickly identify where your software or hardware implementation may have a bug in it. So that's tandem verification. At MIT, that group is particularly interested in formalizations of all kinds, including the projects I mentioned earlier about formally deriving hardware and formally deriving software from the spec. So they also have used it. They've made a connector into the COC tool which comes from INRIA in France, which is the theorem proving and proof assisted tool, and using that to prove correctness of a small compiler. And they're also using it, as I said, for deriving hardware implementations automatically and systematically from the spec. Another aspect of the work with that tool is that in Haskell there is an open source tool available called Clash, which allows you to convert Haskell into Verilog or ultimately into C. And another member of our group, Clifford Wolf, who's also here at the workshop, has a version where he uses a kind of a functional set of Verilog, which can again be converted into C. So he's been running routinely model checking to compare that with the C code that's in the Spike simulator to show that the formal spec and the Spike simulator particularly are in sync with each other. This is done for a small subset of the ISA so far, but over time the idea is to be able to expand this to the whole ISA. Galois, the company Galois Inc. from Portland, Oregon, is also using, particularly interested in security and security properties, etc., which is sort of a layer beyond the ISA, but again, the ISA spec is a prerequisite for that, so they're also a member of the working group and working towards that kind of goal. We haven't done any work at all, I would say, yet on floating point or not, and I'm not very knowledgeable myself on floating point, or I don't think people in our group are very knowledgeable about it, but our hope and expectation is that the aspects about the floating point instructions, which are just about fetch and decode and dependencies between registers, is the same as you would see with any other instructions, and the central part about the computation will be standard IEEE floating point. So we're going to sort of just rely on IEEE as the spec for the functionality of the op, but the rest of it will be covered is in some sense common to other instructions. So our next steps are the following. We've been working now for, I would say, a little over 7 or 8 months in fits and starts. And in keeping with the RISC-V Foundation's objectives of keeping working groups short-lived and focused on particular tasks, there's still a lot of work ahead to do, but here's how we might structure it. Which is to put out a spec within maybe 2 months from now. I think we're close enough to that to be able to say we can do that. Where we do not tackle yet the complexities of concurrency, namely the interaction with weak memory models. Just think of it as sequential instruction execution, but for that model, a very complete and precise spec of everything in the things that you see in the bullet on that in that top box, and call that as the sort of first deliverable of the group. Along with this, we will probably one of the first serious users of this will be the compliance working group, where they will have compliance suites, but whenever they have compliance suites, they are declaring compliance with respect to some golden reference. What will be that golden reference? Well, this formal spec is a very good candidate. Certainly Spike would be another possibility, but again, this would be a possibility for that. So we're in talks with the compliance group all the time about moving that activity forward. And then, given that the top box is in some sense a deliverable, the next, and maybe the final deliverable for the group as constituted right now, the next big task, which is a follow-up, is to then merge together the results of the memory model working group, about which you're going to hear in the next talk, and what we have from this group, to form an integrated spec that covers both the ISA and the memory model. So whether it continues as an activity of the group as constituted now, or we reconstitute another group, which probably will overlap a lot of the membership with the existing groups, but still, technically it might be a new group. That's probably the next big job after this. There's lots of interesting things that can be done with the spec, formally showing equivalences between ISA formalizations, demonstrate extensibility, use it, for example, to specify the vector instructions that were talked about in the last group, and certainly this kind of work on compiler correctness and hardware implementation. So those are my slides. I'll stop now, and we're done.